And now for my take on why did the chicken cross the road. A chicken runs at 4.5 meters per second at 35 degrees across the road. If the feed is 75 meters down the road, which is 45 meters wide, what speed is the wind blowing along the road? I'm going to draw this similar to the way that I drew the last one. So it's a 45 meter wide road. 75 meters down is the chicken feed. And again, the chicken's running at 35 degrees. So how fast is the wind blowing along the road, pushing the chicken sideways? So the chicken is running 4.5 meters per second at 35 degrees along and across the road. So we break that down into components. 3.686 meters across the road horizontally and 2.581 meters per second down. Now, to cross the road, the chicken must travel 45 meters. So horizontally, again, horizontally based on my drawing, the chicken covers a distance in a certain amount of time. 45 meters at 3.686 meters per second. So it takes the chicken 12.21 seconds to cross the road. Now, based on this drawing, the vertical distance, the distance along the road, has a speed total, which is going to be the speed of the chicken, 2.581, plus the speed of the wind. And as we saw in the previous problem, if in fact the speed of the wind turns out to be negative, then our drawing would indicate that it would be going vertically, up instead of down. Distance is equal to the total speed times time. It's going 75 meters. We're not sure what the total speed is, but it takes 12.21 seconds for the chicken to cross the road. So that means the total speed is 6.14 meters per second. So that's how fast the chicken was going along the road. Since the total speed is equal to the speed of the chicken along the road, which is 2.581 meters per second, plus the speed of the wind, so that means then that the speed of the wind is going to be 3.56 meters per second. So in fact, the positive, while the drawing doesn't make any difference, it turns out that the wind is blowing toward the top of the page. And the speed of the wind it's a positive. Sometimes explicitly we would want to put a positive to denote that it's a vector, but it's not necessary in this case since I only asked the speed. If we wanted to write this in terms of a vector more properly, we would say 3.56 j meters per second. Now, it could be in either direction. It really wouldn't make a whole lot of difference based on our drawing and the information that we have. Looking at a more formal definition of vector multiplication, the scalar multiplication is simply taking some scalar r times the vector a, and we multiply each of the vector components, the I component, the j component, and so on, by the scalar r. Vector multiplication, the scalar product, what we commonly call the dot product. What this actually shows us is how parallel two vectors are, or how much of the vectors are in fact heading in the same direction. Sometimes I refer to that as the parallelness. One of the ways to determine, as we did earlier, the dot product is simply by multiplying the corresponding components together. If you don't have it in component form, if you have it in polar form, and you simply need the dot product, all you need to do is take the magnitude of the two vectors and multiply that by the cosine of the angle between them. Now by the magnitude, in this case, we need the absolute value of it. In a perfect situation, two vectors that are completely parallel will have a positive value. Two vectors that are completely anti-parallel would have a negative dot product. Two vectors that are perpendicular are completely not parallel. They're perpendicular, and so they would have a zero dot product. If we compare that to the vector product, what we commonly call the cross product, okay, and that's denoted by the x. If you have it in polar form, it's pretty straightforward in that it's the magnitude of the two vectors times the sine of the angle in between. And the direction is going to be the direction that is perpendicular to both of those vectors. So if we have a vector, for example, one going in this way and one going this way, perpendicular would be going either straight into or out of the screen. So it would be either into, which we oftentimes denote as an X, into, or out of the screen. One of the ways to think about these is you're looking at the tip of the arrow or you're looking at the flight of the arrow. The process of vector resolution is simply breaking the vector down into its perpendicular components, or into a set of perpendicular components. For our purposes, we're simply going to use the x, y, and if necessary, the z components that we're familiar with, but any perpendicular components are fine. You have an airplane traveling 345 kilometers per hour, 26.3 degrees east of south. Now, this notation you will sometimes run into, and you need to get somewhat comfortable with that. East of south, north of west, whatever it happens to be. Resolve the velocity into components, and then determine the components of the displacement after 4¼ hours. So 26.3 degrees east of south. Well, so let's think about a coordinate plane. Down would be our south direction. So east of south would be going rather this way. If we say southeast, we simply say southeast. That implies exactly 45 degrees that we're splitting that quadrant. That's 26.3 degrees here. If it were to be like this, then it would be south of east. And so we would start from our east direction and then move south. And in this case, that should be 63.7 degrees. So now we have a triangle that we can work from. So we have 345 kilometers per hour, and we need our horizontal and our vertical components. So with this being a 26.3 degree angle, this would simply be 345 cosine of 26.3 degrees, and this would be 345 sine of 26.3 degrees. So that's going to give us 309.3, and then this one is going to give us 152.9, and these are in kilometers per hour. So we could, in fact, write the resultant vector, in this case a velocity, using our x and y notation that we would have, 152.9 I plus 309.3 J kilometers per hour. To determine the components after 4¼ hours, all we need to do is do 4.25 times V. So that means that each of our components would work out to be 649 I plus 13414 J kilometers per hour. If we check, we see 3 significant digits in each of these. We're not going to use the angle. And so this one should be 349 I plus 1310 J kilometers per hour. And really this to proper significant digits would be 153 I plus 309 J kilometers per hour.